Hi everyone, this is a video to go over lesson 4.7. I'm going to do this video or this lesson in two parts. I'm going to make the first video just introducing the topic and doing examples 1 and 2, and then the second video will cover examples 3 and 4 because it's quite a big topic. So far in this unit we've been using the first and second derivatives to find information about curves. So for example, finding minimums and maximum points, finding inflection points and concavity. In this lesson, we're going to use the first derivative test that we learned back in 4.3 to find minimum and maximum points, but there's going to be an application attached. So we call these problems optimization problems. And they're solving certain problems where you want to find a maximum and minimum. But like I said, there's some application. Okay, so we're going to start with a really sort of straightforward example here. So we want to find two positive numbers. I'm just going to highlight information whose product is 200 and whose sum is a minimum. So I'm given kind of three pieces of information. I'm looking for two positive numbers. Their product must be 200 and the sum is a minimum. So I've got the steps. Oh, I forgot step 1, right? Define the variables. So I've got the steps to solve these equations written down here on the left, and I'll sort of check them off as we go. At the end, if you want, you can pause the video and sort of write those steps down yourself, because these same 7 steps we're going to do for every optimization problem that we come across. And so we'll start by writing down or defining our variables. So step 1. So I'll just use X and Y because we're used to working with those letters. X and Y be two positive numbers. So I'll just check these off as I'm done. Okay, that one's done. Step 2, write an equation that relates the variables. So given the information, these 3 things I've highlighted in yellow here, we can write an equation that relates these variables. So the product, it says here, must be 200. So X times Y must equal 200. Okay, so you'll always be able to do that. They'll always give you some kind of information about your variables. And lastly, we want to write an equation or a function Q for the quantity we want to minimize or maximize. So the textbook uses Q instead of f of X to talk about this function because it stands for the quantity we want to minimize or maximize, and I kind of like that, so we'll use Q here too. So we want to write Q equals, so the quantity in this example we want to minimize is the sum. So the sum is written X plus Y. So we want to minimize this quantity. And right now, this quantity equation is written in 2 variables, X and Y. This is when we want to go and take the derivative and find the minimum, it's going to be difficult because we've got 2 variables instead of what we're used to, which is only 1. So what you want to do is rewrite your first equation there in terms of one of the variables. So I'm just going to divide both sides by X and rewrite it as Y equals 200 over X. Okay. And I'm going to sub this into the quantity equation for Y. Okay, so since Y equals 200 over X, we are free to rewrite our quantity equation like this. X plus, so instead of Y, I'm going to have 200 over X. Since they're equal, you can do that. Okay, so that's step 4, is rewrite your quantity equation and so you only have 1 variable. That way, when you take the derivative, we can take it with respect to X, and it's easier than dealing with both X and Y. Okay, so now our job is to find the minimum point on this for this function. And we know how to do that. We got to find our critical numbers. So for us, we don't really have any endpoints here, so we're just going to find the derivative. So just a little reminder, critical numbers are endpoints. They are places where Q prime equals 0 and where Q prime is undefined. Okay. So since we have no endpoints here, we're going to find the derivative and see where it's 0 and identify those that could be possible minimum points for us. So before I do the derivative, I'm just going to rewrite this Q function with a negative exponent instead of dividing by x. Take the derivative of that instead of dealing with the quotient rule. Okay, so I'm taking the derivative of my Q function. Derivative of x is 1. The 200 is just a constant multiple, so I'll just pull it out. So now we use the power rule. So the -1 comes down. We have x to the power of -2. I'm going to rewrite this with a positive exponent because they'll be easier to solve for my critical numbers. Okay, so that's my Q prime. And I want to find places where this is undefined and where it's equal to 0. Right away, we can see where it's undefined at x equals 0 because you can't divide by 0, but that is not a critical number. Why is that not a critical number? Well, x and y must be positive. So x equals 0 is not even like a possibility. I'm looking for a positive number. So, but since x must be 0 or greater than 0, this is not considered a critical number. Okay, so I'm just going to look for places where my derivative is 0. So I'll solve for 0. And I'll move the 200 over x squared to the other side. Multiply both sides by x squared. We get 200 equals x squared. And then take the square root. So you do actually get two critical numbers here, plus or minus root 200. Remember, when you take the square root, you need the plus or minus version. So, but only one of those is a critical number. Remember, x has to be a positive number, so we're not even going to consider, x equal, we're not going to consider the -1, is the only critical number. And I'll put in brackets, x has to be greater than 0. Okay, so let's just kind of pause here and review what we've done and check off our next step here. So we found our quantity function that we want to minimize. We found the critical number. There's only one because there's two more possibilities, but they were both outside the domain that we're considering. So I found my critical numbers. Now, if you recall back to 4.3, if we want to figure out if those critical numbers are maximums or minimums, we need to do the first derivative test. So we're going to make a little table and test whether the derivative is positive or negative in the region surrounding root 200. So I'm making a little table here, Q prime and x. So I'm going to look at x values less than 200 and x values greater than root 200. Since I know that at x equals root 200, Q prime is 0. So something less than root 200 is like, I don't know, 10. So 1 minus 200 over 10 squared is 1 minus 2, so it's negative. Okay, you can pick any number you want. And then a number greater than root 200, pick anything, and you'll see that the derivative is positive. That means the Q function is decreasing in this region and increasing in this region. So that means that this must be a minimum point, according to the first derivative test. So we found our minimum, x equals root 200. Great. So we have kind of partially have the answer here. We just have to do one more step. So we found our minimum. And now we just have to find the other variable. Since there were two variables at the beginning, remember y, way back at the beginning? So we just have to solve for y, and then we're done. Okay, so we have x equals root 200. And then y, remember, was 200 over x. So we'll just solve for that. 200 over root 200. So you can leave it like that, or you can rewrite it. It's the same as root 200. So we have our 2 points. root 200 and root 200. Turns out the sum is a minimum when the two numbers are the same. So the two positive numbers that minimize the sum are root 200 and root 200. You should always write a sentence at the end so that I know you understand what your answer means. Okay, done. So let's just take a step back. If you want, this might be a good time to pause and write down those 7 steps, since those are going to be used every single time. And when I'm looking at a test or a quiz, I'm looking for your work to be shown this way too. I need to see you define your variables, write your equations clearly. Everyone should be calling their equation Q so that we're all consistent and that your work is nice and clear. Okay, so we wrote down what we knew about the two variables. Their product was 200. We wrote down a quantity equation that we wanted to minimize. We subbed in one of the variables so that our quantity equation was written only in terms of x. We found the derivative in order to find the critical numbers. We found one critical number. We did the first derivative test, and we confirmed that it was a minimum on our curve. And so we had our answer, and we just solved for the other variable at the end. Okay, so that problem didn't have much context behind it. It was basic because, well, yeah, there's no application really. The next example, we're going to see an actual application to our problem. Okay, so this is a very common optimization problem that you'll see. So it's about fencing. So let's say you are a farmer and you want to put up a fence to make a rectangular field. I'm just going to highlight the important information here. So we have 2,400 feet of fencing in total. We want a rectangular field and it borders a river, and you do not need to fence along the river. We want to know the dimensions of the field that have the largest area. So we want to maximize this time, not find the minimum. We want to find the maximum point per area. Okay, so step 1, define your variables. To do that, you need to draw a picture for this. Okay, so let's draw a really simple diagram. Here's our river. We use blue for river, and here's our rectangular fencing. Notice I did not put a red line beside the river because it says we do not need to fence along the river. And I'll use X and Y again, although you can use L and W if you want to use for length and width of the rectangle. Doesn't really matter as long as you define them. So I'm going to make X the width of this fence and Y the length. Drew that too long. There we go. So let X and Y be the length and width of the rectangle. Okay, so you need a diagram if applicable, and you also need a let statement. Okay, next step, step 2. We want to write an equation that relates X and Y. So what do we know about X and Y? Well, we know that there's 2,400 feet of fencing that we want to use here. So X plus Y, all of those lengths added together should be 2,400. So we have Y plus X, so 2X equals 2,400. Okay, so that's step 2 done. Step 3, write an equation for the quantity we want to minimize or maximize. So in this case, we wanted to maximize the area. So the quantity we want to maximize is, so for a rectangle, the area is length times width. So for us, it'd be X times Y. Okay, that's easy. And then step 4, we want to rewrite our first equation in terms of one of the variables so we can sub it in. So I'll just subtract a 2x from both sides. So rewrite this as y equals 2,400 minus 2x. And I'm going to take that and sub it in for y because I want my quantity equation to be written only in terms of x. That way I can take the derivative a lot easier. Okay. So I'll have x times 2400 minus 2x. I'm just going to expand this before I find the critical numbers. You don't have to do this step, but it just makes your derivative easier. So it'd be 2400 x, otherwise you have to use the product rule, which I don't really want to do. That's 2x squared. Okay, so now it's step 5, find our critical numbers. We don't have any endpoints here, so we're just looking for places where the derivative is 0 or undefined. So the derivative of q prime is an easy derivative. It's just using power rule. So 2400, and then the 2 comes down, so minus 4x. Okay. This is defined everywhere, so the only critical number is going to occur where this is equal to 0. So we'll solve for 0. I'll add 4x to both sides. So I'll have 4x equals 2400, and then divide by x. Oh, sorry, not divide by x. So I have x equals 600. Okay, we don't know if that's the answer yet. Okay, we want to find the maximum point, but remember, once you find your critical number, you need to still do the first derivative test to see if it's a maximum point or not. So I'm going to make a little table, and I'm going to be looking at values less than 600, and then values greater than 600, and I'm looking at q prime here. So you can plug anything less than 600. I'll just plug in 100. When you plug it into q, you are going to, or sorry, q prime, this here, 2400 minus 4 times 100, let's say, that's a positive number. So that means in this region, our q function would be increasing. I'll draw an arrow going up to denote increasing. We know that our q prime is 0 here, and if you plug in something greater than 600, you'll get a negative number. So we're decreasing here. So that means, according to the first derivative test, that this must be a maximum. Okay, just going to make my table a little nicer by adding in a little grid, just so that it looks better. Okay, so we've got our solution, but we just need to find the other variable. So I know the sort of width of my rectangle is 600, but I want to know the length now. So way back at the top, we had written, so x equals 600. That's part of the answer. Now I want to go back, and I wrote down that y equals 2400 minus 2x. So I'm just plug in my answer for x, and I can find y. 600. Y equals, so 2400 minus 2 times 600 is 1200. Okay, so I've got my solution. The width of the rectangle should be 600, and then the length should be 1200. So I'll just write my solution in order to maximize the area, the width of the rectangle, and I'll just make it clear that in my diagram, so I've labeled this x in the diagram, should be 600 feet, and the length should be 100 feet. Notice I've used units in my solution. That's important as well. Okay, done. All right, so those same 7 steps every single time for these optimization problems, okay? So I'm gonna pause it there. So that's the first 2 examples done. I'm gonna make a separate video for examples 3 and 4. If you wanna go and try some of the first few questions before you watch video number 2, that might be a good idea. Okay.